Welcome back to another VESPA tutorial, and in this tutorial we're going to look at the SVD, the Singular Value Decomposition tab. So I'm going to open one of the tutorial datasets. I'm going to go to tutorial number 6, open the dataset, and here's this data. It's a single voxel dataset, and as part of the Spectral fitting tab, we have a sub-tab called SVD filter parameters. And this is the SVD filter. Now, this is mainly used for suppressing unwanted peaks in your spectra as part of their pre-processing. Let me show you how it works. So the SVD algorithm is a mathematical operation which tries to fish out or to decompose your signal as a sum of decaying exponentials in the time domain, or in the frequency domain as a sum of peaks. What this means is that given your spectrum, it's going to try and decompose it into individual peaks. And this is useful if you want to filter out specific peaks. For example, a large water resonance. So here's the SVD view. On the top here, we have the original spectrum. On the middle spectrum here, we see the peaks that the SVD filter recognizes and that we choose to include. And the bottom spectrum shows the difference between the top and the middle. So what we've actually done is we've taken out these peaks identified by the SVD filter. So first of all, I'm going to zoom in a bit, just so you can slightly see better. Here's my spectrum. So you see the Na singlet, the creatine, the choline, and water should be at 4.7 ppm. And actually, when we look at the original spectrum, it has a large water peak at about 4.7 ppm. And if I just zoom out vertically a bit, you can see it's not a very nice looking one. It kind of has a bump here. So it's not a really nice Lorentzian ideal water peak, but we'd still like to filter it out. So this SVD filter can be used for that. Now, once the filter is run, and you can do this, it actually runs automatically once you start it, but once it runs and you feed it number of data points in exponentials, and we're going to go over in a moment what these actually do and what they mean, the filter spits out a set of peaks that it identifies. You see that there are 20 exponentials here, and our list of peaks has 20 entries. So this means that this SVD filter is trying to decompose our signal, our spectrum, into 20 Lorentzians. Now, our spectrum might have many more, but this is what the SVD thinks it should do. So it kind of tries to find the 20 most dominant Lorentzians in the spectrum and say, okay, here they are. Now, just counting, we can sort of guess that we'll have one Lorentzian representing the NAA, another one for the creatine, for the choline, for the second creatine peak at 3.9, and then for the myo, and maybe it looks like we're going to need maybe 2 or 3 Lorentzian peaks for the water. So they slowly add up, but just visually inspecting the spectrum, it looks like we can get away with 20. So here on the first column, the rank, we can select which peaks we want to include in the middle spectrum. And each peak, as you can see, is characterized by a bunch of parameters, being the ppm, the central frequency of the peak. Here it's in hertz, the damping coefficient, basically like an effective T2, but not in units of T2, the phase of the peak, and the total area of the peak. Now, these peaks here at the bottom, 17, 18, 19, 20, which are checked, actually probably correspond to the water peaks. Actually, maybe not this one, because let me just take it off. because these peaks are close to 4.7 ppm, so they're probably water, and we'd like to include them. All of the others that are far away are not. So let me just untick these. You just see that the peaks here in the middle spectrum have disappeared. I can add them back in, and it looks like the SVD filter approximated the water peak using 3 Lorentzians. Looking at the bottom spectrum, which is the difference between the top and the middle, or the original and the selected SVD filters, we see that this filter has actually done a very good job of removing the water peak without visually substantially impacting the other peaks. So it works really well, assuming that you've selected the correct peaks and played around with the parameters for a bit. Now, for example, I can scroll up a bit. You can, by the way, you can sort this according to frequency, damping coefficient, phase, whatever you want. I'm going to sort it by frequency. And for example, looking at this peak here, number 4, I see there's something at 2.02, and this is probably the NAA singlet. And I can turn it on, and you can see that here it is in the reconstructed SVD spectrum. And actually, when we look at the bottom spectrum, we see that the NAA peak has disappeared because we've basically chosen to exclude it. So in a sense, the SVD algorithm is kind of a mini fitting algorithm. It's not a real fitting algorithm because it's a model-free one, and it doesn't really make the connection between the size of the peak and the amount of metabolite. For example, if you get a J-coupled peak that's split once, it's going to appear as 2 different peaks. And this SVD algorithm is going to try and fit them or display them as 2 individual components. But what you actually wanted from a fitting algorithm is for it to recognize them as 1 metabolite. So this is not really a certified fitting algorithm, but it's definitely an excellent tool for picking out particular peaks that you don't want and just filtering them out. And I can try and maybe filter out the lipids. You see there are some lipids here, I'm guessing at 1.43 and some unknown resonances below that. So let me check these out. See, I can just tick them, and it kind of recognizes the lipids here to the right of the NAA and does a good job of removing them in the spectrum. Well, let me untick the NAA. See, NAA is back in the spectrum now, and our spectrum looks somewhat nicer. Now, a few words on the selection of parameters here. You can either select peaks individually by checking the box. You can select peaks by moving the cursor or selecting a region with the cursor. Sorry, let me zoom out. And you can select peaks by their distance from 4.7 ppm. So by selecting threshold, everything that's 11 Hertz or less away from 4.7 ppm gets included, which will probably be the water. For some odd reason, this peak here at 7.5 ppm is getting included. I'm not entirely sure why. You can turn all peaks on, which kind of tries to once again decompose our spectrum as a sum of Lorentzians. You can turn them all off, which basically means that you're doing nothing. I'm going to go for threshold. And just a few words about exponentials and data points. First of all, make sure that the number of exponentials that you use is kind of like, it's on the order of number of peaks you'd expect in a typical spectrum. So 20 is a good number to start with. You can see what happens when you reduce it. And this algorithm works in real time, so it's fast. And it's nice because you can play around with the parameters fairly easily. So you can see that even if I reduce the number of exponentials quite substantially, I still get pretty good water suppression. Now I'm at 5 exponentials. and it's trying to model the water as 2 Lorentzians, and it's really doing not too bad of a job. So 20 is definitely a good starting point. Data points means how many points from your FID you want to use to estimate the Lorentzians that make up your spectrum. Use too few and the algorithm doesn't have enough data to work with. Use too many and you're introducing probably too much noise and making the estimation a little less accurate. Okay, I can just pull it up all the way here to 4096, and it actually works fairly well. It's pretty robust. It still makes out the water peaks, but it's probably a good idea not to use too many, just so you don't introduce noise, and maybe for larger data sets it makes the processing slightly faster, but not substantially. So this is it. This is the SVD filter, and use it to take out unwanted peaks in your spectrum, or as a very, very crude fitting algorithm. Although once again I have to say it's not a real fitting algorithm. A real fitting algorithm needs a good model, but maybe as a good starting point for some of the guesses that will come down the road.